Hello everyone and welcome to the next part of surface hydrologic modeling discussion. This is one of the favorite topics because if you recall the definition of GIS, what we had in that after all this development of database and everything, we would like to do the modeling, and this is what we are doing here. So, this is the ultimate, and the modeling allows us to do the prediction. So, nothing is happening on the ground, but we are predicting the drainage network, we are predicting the watershed boundaries and many other parameters which we will also see in this discussion. So, it is a ultimate aim of a GIS project is to model something, present different scenarios for the decision makers, and therefore, GIS is also a decision support system. Now, the next theme or next output or derivative which we drive through this surface hydrologic modeling is called the flow length. So, flow length is basically an arbitrary pixel which is determined by summing the incremental distance, and that distance is from center to the center of each pixel or each cell, because here we are using digital elevation model. So, instead of pixel you can use word cell more appropriately along the flow path, and flow path we have already discussed, that is the drainage network from the selected cell to the outlet cell, and this is what we will be doing in the flow length. Flow length is the upstream or downstream distance or weighted distance along the flow path for each cell. And this primary purpose or use of this flow length tool or flow length derivative to calculate the length of the longest flow path within a given basin, because this is very helpful while doing the modeling for the flood. How much time water will take to reach to the outlet or any other location within a basin, that will depend on the flow length, how much distance it has to travel. So, that we can determine through this step in surface hydrologic modeling, and this flow length is often used to calculate the time of concentration of a basin, which is directly linked with the your flooding forecasting. Also may be related with sediments flow or maybe some other pollutants, because this is after all time of concentration, how much time it would take to reach a particular location. And this flow length will be derived using the upstream option similar to flow accumulation as we do. And this because it is a sequential processing in surface hydrologic modeling. So, this is basically a fifth step in surface hydrologic modeling, or this tool can be used to create distance area diagram of the hypothetical rainfall and runoff events using weight raster as an impedance to the movement of the slope. And now this weight we can based on the land use conditions, the weight can be assigned or impedance can be estimated, and that will allow us to do this modeling more accurately, more realistically. So, this flow length can also be used to create distance area diagram of hypothetical and downslope. Now, this is the flow length of the same digital elevation model which we have been discussing in this discussion also. Drainage network with the stream ordering is also shown as a stellar stream, and these are the flow length here is shown in the downstream. So, as you can see that here for example, the values would be very less say in this part, but as we go in the downstream the length increases. So, therefore, there are for each cell the changes are occurring. It is not necessary that we always see, because it is a raster. So, it is not only along the drainage the flow length is calculated, but for each cell it is calculated. As you can also realize that these are the boundaries which are being formed here. Ultimately, they may become our watershed boundary, that is a different thing. So, we can extract the boundary, a watershed boundary as is here using some other tools like delineation of watershed, again using a surface hydrologic modeling, deciding this is my outlet. As you can see here, the low values, the colored values are having a relatively very large value as compared to the one which you are having here. Sorry, low values as compared to the one which you are having high. So, naturally the flow length from this point to the outlet is much higher than from this point to this point. So, that will allow us to estimate the time of concentration, especially related with water or sediments. And also we said, they say that we can prepare a histogram of time length versus that how many cells will contribute, and that will let us know that if this cloud burst happens in this part, then how much time it would take to reach, what would the flow length, how much travelling time it would require, that can be estimated very easily. This is how it is used in the modelling. Now, flow length of the downstream flow length, the minimum flow length flow would be at the pore point, outlet of the watershed, and maximum would be the watershed boundary. And generally the flow length assigned to the outlet cell, which is 0. So, whenever there is a precipitation in form of rain, a drop of water landing where in the basin must first travel some distances before it is reaching to the outlet, and that will be decided based on the how much travel it has done. So, if we assume that this constant flow velocities, generally in the modelling some assumptions will always be there. So, here if we assume that the velocity through this travel path is the constant, which maybe we will relax later, the pixel or the cell with the greatest flow length to the outlet represents the hydrologically most remote pixel or remote cell. Is flow length divided by the flow velocity represents a representative lag time for the basin, and the lag time quantifies how long before the entire basin is contributing to the flow, because each drains will not reach, or each drop of water will not reach at the same time at the outlet. So, there will be some lag time, and that too can be calculated using flow length. Now, the sixth one is the watershed delineation or delineation of watershed boundary, which is determination of contributing area above a set of cells in a raster, that is our digital elevation model. So, the only requirement here is to deciding the outlet. Once the outlet has been decided, pore point, then the watershed can be delineated using the flow accumulation theme. So, basically if we want to define watershed in terms of in surface hydrologic modelling point of view, then a watershed is the set of all cells whose downstream flow path passes through a selected outlet cell, and the value of each watershed will be taken from the value of the source in the input raster or feature pore point data. The same digital elevation model which I was using, the watershed has been delineated, and the condition, the threshold value was kept equal to more than 500 cells. So, any watershed which is less than that has not been identified. One problem I mentioned earlier also in the previous lecture, which I am going to repeat, that while doing this thing you will have problems or limitations of this surface hydrologic modelling along the boundary or margins of your input digital elevation model, which you can see. Because remember, one watershed ends, another starts. So, here we do not have a continuous digital elevation model for the entire globe, only a part of here. So, wherever that means this area is will contribute to some other outlet, not here, but some outlet, maybe like this, and therefore, it is not part of this basin, and therefore, it has not been delineated. Similarly, in all boundaries area. So, that means the water will flow out from like this, from the same here also. So, if you are working for a real project, it is always good to take a large area. This I have been also telling in case of interpolation or any other thing. Take little larger area, so that then you later on you can make a subset. Otherwise, you may have this kind of limitation of surface hydrologic modeling. So, boundary issues will always be there. Anyway, the watershed interactively also you can delineate the watershed with choosing a single watershed has been used by choosing a outlet or pour point here. And of course, in the background your flow accumulation, which is the basic theme required for delineation of watershed, was shown there. Now, delineation of sub watersheds can also be done. Here also these can also be considered sub watersheds, which are small, but if this is the outlet, these are the sub watersheds, and overall this is the watershed for the entire input area. That means a large watershed can have many sub watersheds, or you can say each stream segment will have its own watershed. Threshold value was kept here 500 cells. If I change the threshold value to 1000, then number of watershed will reduce, however their areas will increase. So, many watersheds which were too different here like this, they are still there, but here they all have been merged small one, and because I have put the condition more than equal to 1000 cells. So, if this is the condition, small watershed will disappear. Now, there are other uses of watershed characteristics which we can utilize, and like for example, important characteristics like for this thing like size, shape of watershed, physiography of the watershed, climate. Physiography will include minimum, maximum, what are the slopes and other things. For climate studies, for drainage studies, for land use studies, for vegetation, for geology and soils, hydrology, hydrogeology, and this is believe me, this is not exhaustive list. So, there can be many other things which we can use, or we use for watershed characteristics, we are used for different studies. Now, once you have delineated a watershed or ask a system through surface hydrologic modeling to delineate watershed automatically by providing this threshold value, many other parameters related with watershed can also be derived automatically. So, automatically you can derive, for example, area of watershed you can calculate, the perimeter of the watershed, the centroid, because it is a polygon. So, you will get area, you will get centroid, also mean elevation, mean slope, highest elevation, lowest elevation, that is all going to be always pour point, and then stream flow, stream length, shape factor. Shape factor plays very important role in your flood modeling, because if a watershed is having a shape something like this, and this is drainage network, that means there will be lag time more, and that means if water is falling all over this catchment like this, or watershed like this, then the water which will fall here will come out first of this outlet, whereas water which will fall here, precipitation which will occur here, will come out last, because therefore there will be lag time, that water falling at different basins will come out within that basin will come out differently at different times. Flow length is different, but if watershed is having a circular shape and outlet is like this and drainage network is something like this, then what would happen, that every stream will contribute to the water at the almost same time here, and then there will be flooding in this part. Therefore, the shape of watershed really matters a lot for flood modeling, and of course, then other related things like sediments and other things will also come. So, there it is very easy using surface hydrology modeling to drive all other parameters which are required for various studies of watershed. So, there this is again not exhaustive list, many more parameters can also be derived. For example, you can the characteristics, water set characteristics which are used in engineering or in sciences like earth sciences, hydrology, like drainage area, again very important. Then that is the area which is being covered, because most important for hydrologic design, reflects volume of water generated from the rainfall. The volume of water available for runoff may be assumed as the product of rainfall and drainage area. Drainage area input to all models, which is always required. Now, watershed length, that is the increases as the drainage increases. So, L is important in hydrologic computation. The L defines a distance measured along the main channel from the watershed outlet to the basin divide, and this L measured along the principal flow path, as I shown through earlier through the shape of watersheds. And then both A and L measures the watershed size. They may reflect different aspect of size. A delineate potential of rainfall to provide a volume of water. L used to compute the time parameters, measure of travel time of watershed through a travel time of water through a watershed. Watershed shape I have already discussed, which plays a very important role in flood magnitude assessment, and then of course the slope will also play a very important role. And here we can utilize this one like S equal to the delta E upon L, and whereas E upon L, the delta E is the difference in the elevation between the elevation difference between the end point and the principal flow path, and L is the hydrologic length of the flow path. And watershed shape, which is also very important, we have already discussed this, because bunching up of water should not happen within one watershed. Though nature, this is a natural boundary, we cannot change, but if impedance can be provided, then all the water which is falling over a watershed will not reach at the outlet at the same time, or will not get concentrated in one area of watershed at the same time. Channel length also used in hydrologic computation, that is the distance measured along the main channel from the watershed outlet to the end of the channel. Channel slope is also very important, which can be calculated like this. And if a channel slope is not uniform, naturally, generally it is not, in nature it is not. There might be rapids, there might be a flat part and so on. So, a weighted slope may be provided an index, that is why the slope, channel slope is very important. The effect of slope on the hydrologic response of the watershed. Each parameter will play their own important roles. Now, there is also automatically you can delineate the drainage network through a raindrop simulation, or also it is called shortest path route or routing. If I drop a single drop of water like this here, then over a flow accumulation theme, it will show that which path it will follow to come out of this outlet. So, this you can do it once you are having flow accumulation theme as a drop simulation. Now, major use of this in related with point source pollution studies, or also in use for estimating for groundwater recharge or other things, that which stream will take, and of course, the time and length everything can be then measured, because every data is here itself. So, once you know the velocity, the time can also be. So, the traces, what is basically raindrop simulation, that is the traces of flow path of a point on a surface grid theme, thus input is flow accumulation. As I have already mentioned, very useful for point source pollution studies. So, employing two themes together, flow direction and flow accumulation processes, it is easy to compute a mass balance of each cell in terms of S equal to P minus I minus F minus E, where S is the surplus water per cell, P is the input precipitation, F is the infiltration, and E is the evaporation. Because more the realistic picture you want in a modeling or more better prediction, you have to bring other losses of the water, and here it is coming in form evaporation or evapotranspiration, which is going to the atmosphere, infiltration which is going downward towards the groundwater, and of course input is also there. So, this cumulative flow over the net is then obtained by accumulating S over the flow direction grid, this S. Now, there are predictive equations are another way to use for map overlay, depending on for what purpose. For if I want to calculate for water availability, for runoff equation is used for by the hydrologist to calculate the amount of water that will be available for runoff for a specific runoff rainfall event based on the type of soil and land cover present at a location. And this information can also be used to predict the amount of water available for runoff at every cell in a water set, and this could then be accumulated across a flow direction surface. And very important to the road engineers who has to design a road that crosses that drainage, because in flood events the minimum damage or no damage should occur, and therefore in the design, while designing these things and these either small bridges or culvert or whatever, these things should be kept in mind. After all, if they put in a culvert, then too small, there could be a problem. So, if estimations have been done properly through surface hydrologic modeling, then a proper design of culvert will come or a bridge. Now, how you will calculate the availability of water for runoff calculation, which accurately if we want, then you have to bring the soil hydrologic soil groups as one of the inputs, land use land cover map, rainfall precipitation data, and all these will be combined. Then you will have the curve runoff number, surface runoff number SCN method, and then you will have the water available for runoff, your elevation, that is a digital elevation model, field depression, sinks, flow direction, which is also combined, and finally you come to the accumulated water available for runoff. So, these calculations are very, very important from flooding or other modeling point of view. There may be many other types of hydrologic variables that can also be generated using digital elevation models. In this course and in limited time, we have touched only few. When we started discussing digital elevation model, at that time I mentioned that digital elevation models and satellite images are a storehouse of information. As we are moving and advancing, we are taking out many other informations from these two major sources. Flow direction grids are basis for a wide range of dynamic modeling tools, where we keep changing and as per the conditions, prevailing conditions, current conditions, things can be. Now, another derivative which is again important, which is topographic wetness index, TWI. Again it is a output of a surface hydrologic modeling using a digital elevation model, which is also called as compound topographic index, CTI, is a steady state wetness index. And in some areas this TWI, that is topographic wetness index, has shown in some studied areas to predict SOLUM, the surface and subsoil layers depth. And it involves the upslope contributing area, that is A is slope raster. Of course, you are already having a slope map and derived through a digital elevation model, and a couple of geometric functions. This is the output based on the same digital elevation model about the topographic wetness index. As you can see that darker here the main higher order streams, you are having this wetness much high naturally, and there are areas where the values are very less, which are shown here in light pink color. Application areas of topographic wetness index are a runoff, flood, erosion, etc. So, when you calculate this topographic wetness index, the value of each cell in the output raster of topographic wetness index or TTI is the value in a flow accumulation raster for the corresponding DEM. And higher CTI or TWI means that values represent the drainage depressions. Obviously, these are the drainage lines which are shown here in the dark maroon color. Lower values represents the crest or ridges, as you can see if I draw here, and then roughly these are the ridges which are here. Now, another derivative is the sediment transport index, which is a movement of sediment typically due to a contribution of gravity action on the sediment or and on the movement of fluid in which the sediment is entrained. The sediment transport occurs in natural systems. So, in a natural drainage system there will be some sediment. The density or the turbidity may vary, but there will be some particles in suspended form or may roll along the stream. So, where particles are clastic rocks, can be clastic rocks, sand, gravel, boulders, etc., or can be very fine one, mud or clay, or the fluid in the air. Water or ice force the gravity acts to move particles along the sloping surface on which they are resting. Sediment transport due to fluid motion occurs in rivers, oceans, lakes, seas and other bodies of water due to current and tides. So, in almost all along water bodies or at the margins of water bodies, transport or this transport of sediments can be visualized. Now, in this sediment transport thing, which is again the same input digital elevation model, you are seeing here light colored one are showing the less index value, and whereas the dark one are showing high index value. And application of this is mainly in the soil erosion studies. So, sediment transport index characterizes the process of erosion and deposition. So, wherever you are seeing all this dark areas, basically they are indicating the depositional areas. So, presents the effects of topography on the soil loss and can vary along the length of a stream, of course. Now, this STI, that is sediment transport index, is important in many other studies, including in sedimentary geology of part of earth sciences, geomorphology, civil engineering. There is a link, especially in hydraulics, civil engineering with the geomorphology, and also in the environmental engineering. The sediment transport plays very important role. So, this knowledge of about a basin or a watershed, if we are having about the sediment transport, can be used to determine whether the erosion or deposition will occur, and the magnitude of this erosion, deposition and the time and distance over which it will occur. Suppose on a Himalayan regime, Himalayan terrain, you are having a large reservoir, for example, a Tehri reservoir. Now, you would like to estimate that what kind of sediment will be coming in the reservoir, because you know that more the sediment will come in the reservoir and settle down, it will reduce the capacity of the reservoir, storage capacity, and ultimately it will reduce the production, power production from that reservoir. So, estimating sediment transport is very important from that point of view. Stream power is the rate, another product which is the stream power index, which is the rate the energy of flowing water is expected on the bed and banks of the channel. How powerfully, what is going to be the velocity or power of flow along the stream or in the margins or in the banks, and it is the potential of flowing water to perform geomorphic work. Geomorphic work the basic work are erosion and deposition, which creates different landforms. And stream power can be calculated again using a digital elevation model. So, that is also one of the derivatives. Now, stream power index, or we can also call it as SI, can be used to describe potential flow erosion and related landscape processes. This can be calculated as SI equal to CA multiplied by G, and whereas CA and G are specific catchment area and gradient repeated respectively. So, a specific catchment area and gradient increase, the amount of water contributed by the upslope area and velocity of water will also increase. So, there is a direct relationship. Hence, stream power index and erosion risk increases. Whereas, the stream power index controls potential erosive power of overland flows, thickness of the soil horizons, organic matter, pH, silt and sand content, and obviously plant cover distribution that will create impedance. So, for a realistic picture, everything has to be included, including land use and forest cover and vegetation, everything. Of course, slope will play also very important role, and soil type and geology and other things. Now, this is again digital elevation, same digital elevation model was subjected to stream power index. You can see that here the stream power is very much high relative to other parts of this water side. Here when we are seeing visually we are finding that this area is having almost same value, it is not true. There are values which are varying. If you zoom it and use the identification tool, you would find that each cell is representing a different stream power index. So, basically stream power index is a indicator of erosive power of overland flow, that is surface runoff. That means we can drive lot of derivatives from digital elevation model. It depends on for what application I am working. If I am working for say for example soil erosion studies, I will involve those kind of derivatives. If I am working for this flood monitoring or flood forecasting, then I will use those parameters. But the input is one digital elevation model, basic input, and there can in order to have more realistic thing or modeling, we may include some other themes or inputs like land use, land cover and so on. So, this brings to the end of this two parts of surface hydrologic modeling discussion. With this I thank you very much.